Continue on with chapter 8, and we'll start talking about fracture mechanics. All right, so let's first go ahead and take a look at brittle fracture and the Griffith criterion, which is equation 8.3 in your text. I'm just going to give you a little bit of background here, a little derivation for it that's not included in your text, just so you can kind of see where this equation comes from. So the idea here is that we're going to have a crack in a material, and this crack is going to have a length A, as shown here, and then the crack will advance some distance delta A. And when the crack advances that delta A, it will release the strain energy in the material around the crack, and it does this, shown here is in kind of a circular geometry. It's not quite circular, but it's a reasonable approximation for what we're doing. And so this area here, this is the new energy that's been released, the new elastic strain energy that's been released as that crack advances forward. Okay, now that elastic strain energy is basically given using Hooke's law and taking a look at the area under the stress strain curve. And so if you think about the stress strain curve, and we have Hooke's law, then what we're looking at here is an energy or an area of 1/2 stress times strain. And then we know that the stress is equal to the elastic modulus times the strain. So if you go ahead and substitute in for the strain here, then you'll get the elastic energy is equal to the stress squared over 2 times the elastic modulus. And that's an energy density and energy per volume. Okay? And so that's the amount of energy that gets released. And so that's what's driving the crack to move forward, right? To release this strain energy. When it does that, though, it's creating 2 new surfaces of length delta A. And we've learned that surfaces were defects, they cost energy. And so if we have a surface energy term, and we've talked about that a little bit, different faces, for example, have different surface energies. If I take that surface energy and I multiply it by 2 times the crack length A, that's going to be the total surface energy that's there due to the surfaces. There's 2 surfaces, each length A long. Okay, this is the total energy for the whole crack. The amount of energy that's released in that one little step then would have been 2 times delta A times the surface energy gamma. Okay, but we're going to write the whole surface energy out just like we are with the elastic energy. We're going to go ahead and multiply that by the whole area or volume if we go ahead and take into account the width of the sample for the energy release rate. So this represents the total elastic energy released. This is the energy that it costs us in creating those new surfaces. And so the total energy change in our system then is just adding those 2 terms together. And then what we can do is take the derivative of these 2 terms. This equation, if we were to plot, it's going to have a maximum in it, right? And we want to find out where this maximum is. Okay, this will be like the equation for energy you're plotting versus crack length A. So we'll go ahead and we'll take the derivative with respect to A, set that equal to 0. And then when we solve, we get out the Griffith criteria. So this is going to tell us the stress needed at this maximum for the energy to then start to drop if the crack advances in length. Okay, so that becomes a critical crack length or a critical stress. So if we were less than that stress, or we had a crack that was smaller than that value, then the energy gets lowered by shrinking the crack, and so the crack would close. So that's the idea. Okay, so this was Griffith's criterion 8.3 in your text. And all we need to know then about a brittle material is the elastic modulus, the surface energy, and then the size of the crack or the stress that the crack is seeing. All right, so let's go ahead and use this as a quick example. So let's say we have a large plate class and it's subject to a tensile stress of 40 megapascals. So 40 megapascals is applied to this cracked sample. We're given the modulus of elasticity of 69 gigapascals, and we're given the surface energy of 0.3 joules per meter squared. And we want to know what is the maximum length of the surface flaw. Okay, so here we are at the surface and we have a crack of length A. So what is the maximum length for this flaw that's possible without fracture? Okay, so I've got my fixed now stress that's being applied, and I want to know how big my crack can be to avoid fracture. So we'll just go ahead and rearrange that. Then for the critical crack length, we'll substitute our values and we get 8.2 microns. So any crack size that's greater than 8.2 microns would immediately fail in brittle fracture, and anything less than 8.2 would close or would not result in a brittle fracture. It'd be stable. All right, so this brings up the idea of a stress concentration. So let's say that we have a sample that has a hole in it. This could be an elliptical hole, could be a circle, or eventually we're going to make this a sharp crack. But let's say we have an elliptical hole with a radius of curvature at the edge, and the radius of curvature you can just think of as the size of a circle here that would fit into this lateral location on the ellipse. And this is defined here as rho. Okay, if this was a circular hole, then the radius of curvature is just the radius of the circle. All right, so we have an applied stress to the sample, right? And what happens is that right at this location here, these lateral locations, we're going to get a concentration, this one here as well. We're going to get a concentration of stress. These edges are going to feel a much higher stress value than the applied stress sigma 0. And this is given by the equation that's shown here, where A, again, is the crack length, rho is the radius of curvature, and then sigma 0 is your applied stress, and then sigma m is that concentrated stress at those locations. So if we wanted to look at a stress concentration factor, we could just divide that stress there at those lateral locations divided by the applied. So we would just have this term here. Let's say that we have a flaw that's a circle, and in that case, the crack length A is equal to the radius of curvature. And so this term becomes 1, and we'd have then that our stress concentration factor by that equation is equal to 3. So for the circle, we've got a stress concentration at those edges of 3 times the applied stress, and quite significant. Now, as that becomes an ellipse, as shown here, that stress value, that concentration goes up. As you eventually get down to the crack, you've got extreme concentration values there at the crack tip, and we'll talk about that in a bit. All right, let me say a couple other things. This value A for the crack length, just notice by definition, A is the crack length if it's at the surface. If it's an internal crack, the internal crack length is 2A. Okay, so if a problem says that you have an internal crack of 1 millimeter, just write this down. So let's say you have an internal crack of 1 millimeter, then your A in this case is 0.5 millimeters. Okay, I know that seems trivial, but this is really easy to mess up in the calculations. So an internal crack is defined as 2A. Okay? Do not modify the equations. For some reason, there's always this desire to put a factor of 2 somehow in the equations. Don't do that. It's the value of A that you're putting in that changes. Okay. All right. So let's take a look at the stress out front of a crack tip now, where we start getting much higher stress concentration values. So let's say that I have a crack here of A, and it's a sharp crack. These lines here represent lines of stress. Okay, these are stress lines. It's referred here to as lines of force concentrated at the crack tip. It's our stress concentration. As we, and you can think of this as a topographical map. So when I get a lot of these together, then this means that that stress value, stress intensity is increasing. Okay, so I have a lower stress out here, far from the crack, and I've got high stress as I get close to that crack tip. And that's what we've got plotted here. Okay. So far from the crack tip, we're just going to get the remote stress that's being applied, sigma. And then as you move to the crack, you're going to get this very rapid rising local stress to this crack tip. All right, so the equation for that is given here. So you can see that the stress falls off like 1 over the square root here of the radius. And that local stress is proportional to the square root of the crack length. And of course, the applied stress. And then we'll talk a little bit about this geometric factor in a minute. All right, so this leads us finally to a definition for a fracture toughness of a material. So now we're going to get to an actual value. We can assign a toughness value to a material rather than just referring to some materials as being tough and some as being brittle. Okay. So one of the things we want to notice is that out front of a crack tip, that intensity that's there is going to scale like this top piece, right, where this bottom term represents our position out front of the crack. And so if we just take a look at this top piece, we could define that then as the stress intensity. This is the multiplicative factor here that's raising the stress. Okay, it represents how bad this crack situation is, okay, how high this crack intensity is. And so when this now reaches a critical value, we get fracture. And this critical value we can define here as a fracture toughness. So this would be the material property, fracture toughness. And when it's when this stress intensity here equals the fracture toughness, then we're going to get fracture. Okay? Or if you want, we should really say that as this value is greater than the fracture toughness, we have fracture. Right? If the value is less than the fracture toughness, then we have no fracture. So in that case, the crack tip might blunt out and have plastic deformation, but it won't fracture. Okay, so I'm going to stop there because what I want to do is take a look next time a little closer at this fracture toughness value, talk about the case for plane strain fracture and a specific mode. And so we're going to do all that next time and run through an example.